Okay, good afternoon, everybody, and welcome to the Construct Innovate webinar series in association with Engineers Ireland West Region. This is the webinar series on sustainability planning and construction. My name is Jamie Goggins, and I'm Director of Construct Innovate, which is Ireland's National Research Centre for Construction Technology and Innovation. So this is the second week of the webinar series, and this week we are concentrating on carbon footprint, so identifying hotspots and reducing greenhouse gas emissions associated with construction. We're going to have three speakers today. So our first speaker is Dr. Thomas Adams from the University of Galway, and he's going to talk about the what and the why of carbon footprint and give some example case studies. Then we have Dr. Richard O'Hegarty, who's research lead at RKD and also is a researcher at University College Dublin. And he's going to talk about decarbonising concrete today, tomorrow, and to 2050. So Richard worked as part of the team that helped the government in terms of their requirement to decarbonise the construction sector and the requirement to use low carbon construction materials, in particular concretes and cements. And then we were to have Stephen Barrett, who's the whole life cycle carbon lead from the Irish Green Building Council today. But unfortunately, Stephen wasn't available due to personal commitments that he had to do at the last minute. So we're very grateful to Dr. Paul Moran, who's Associate Professor from the University of Galway, who I rang 8 minutes ago to come in as a substitute, and he's going to do a presentation on the assessment of whole life carbon of case study buildings in Ireland using the Indicate tool in there. So we'll have the three presentations and then we'll have Q&A afterwards. So if you have questions for any of our speakers, then post them into the Q&A function. So you'll see the little icon for the Q&A at the bottom of the screen. So please post your questions there, and we will deal with the questions at the end of the presentations in there. This webinar is being recorded and will be made available afterwards online. So without further ado, I'm going to hand over to our first speaker. So our first speaker, Dr. Thomas Adams from the University of Galway, on the what and the why of the carbon footprint. So over to you.
So yeah, I'm Thomas Adams. I'm just coming up to the end of my PhD in civil engineering at the University of Galway, and it was on the topic of sustainability reporting. So kind of a subsection of that I'll be talking about today is carbon footprinting, looking at the what, the why, and kind of the how of the carbon footprint, and some examples and case studies from the construction industry. So just an overview of the presentation, first looking at what is a carbon footprint, some kind of global and Irish overview of the whole emissions kind of picture, looking at what does a carbon footprint measure and comparing it to life cycle assessment, and then a sample carbon footprint report, how to measure and what comes after you measure. So first of all, just at a very basic level, what is a carbon footprint? So a carbon footprint is a methodology to try and capture all of the greenhouse gases that are emitted from activities that we do. So this graph here on the left first shows the four main greenhouse gases, obviously carbon dioxide, and then methane, nitrous oxide, and fluorinated gases. And the way that the arrows kind of jump in size represents how much heat each of these gases trap. So carbon dioxide actually traps the least amount of heat, followed by methane, nitrous oxide, and fluorinated gases trap loads of heat in terms of that greenhouse gas effect. But then you see the pie chart beside here shows why we call it the carbon footprint is because carbon dioxide is the one that we emit the most by far. So that's the idea behind the carbon footprint, is just a way of measuring these different greenhouse gases. They're also converted back into one unit of carbon dioxide equivalent, which is why we call it the carbon footprint. Methane and nitrous oxide and fluorinated gases, we convert them into carbon dioxide equivalents. So we have this one unit of measuring the global warming potential of our activities. This then is kind of an overview of the global greenhouse gas emissions. So this is actually from 2016. It's probably changed a little bit since then, but it'll just give you an overview of kind of the different activities that we do as humans that emit these greenhouse gases. And then I have some bullet points here on the left that kind of just link the main ones to the construction industry. So looking at kind of energy use in industry, you see the first chunk there of iron and steel is 7.2%, is pretty significant and fairly related to construction. You'd think it then energy and transport, transporting construction materials to and from sites would be fairly significant. And then the big chunk of energy use in buildings Obviously, that would be the operational use of the building rather than the construction of, but that's of course affected by how energy efficient we build our buildings and how we use them. Looking at the small industry chunk there, 3% of that 5.2% is just cement. I'll let Richard go into more detail on that later, but you can see how cement makes it onto this big picture of everything we do. Cement is 3% of that big picture. And then waste, if we put our waste in landfills, it can be fairly significant. And also deforestation in some cases can be related to construction. Looking at the kind of big picture in Ireland's case then, so this is the 2023 overall carbon footprint of Ireland as a country. You can see agriculture has that big chunk. As we all know, agriculture is the main kind of source in Ireland, followed by transport and energy industries. And I kind of thought the table on the right here, if you see the green shows that it was actually reduced from 2022 to 2023. And overall at the bottom, you see that we actually had a relatively significant drop in emissions on a national scale for the first time. I do think we had a drop the year before, but it was only about 1 or 2%. And this time there's been, whether or not you include land use change, the LULUCF is land use change and forestry. So obviously something went wrong in the way that we manage our lands there, that we had such a big jump from our land use. But overall, there was a 4 or a 7% drop, depending whether or not you include land use. So what is actually measured in a carbon footprint then? So this is according to the Greenhouse Gas Protocol Corporate Standard, which is kind of the most commonly used standard globally for measuring the carbon footprint. And it groups emissions into these 3 scopes. So scope 1 is fuels burned directly on site. Generally, that is mostly heating fuels or company vehicles or machinery that burn fuels also. Scope 2 then is purely just electricity that you purchase from the grid. It's called indirect because the emissions aren't coming from on site, they're coming from wherever the electricity is produced. And then scope 3 is all other indirect sources of emissions. And the main ones here would be purchased goods and services, which is essentially the supply chain for your company. So materials, products, and services that you purchase, and the emissions that are associated with buying those things. Another significant one then is travel, which would mainly be how employees get to and from work, but also if your company funds a lot of business travel, that can be significant too. Waste, as I was saying, if it's sent to landfill, that has a pretty significant carbon footprint associated with it. And then also transport and distribution, particularly for the construction industry, moving heavy materials to and from site can have a pretty big footprint also. Comparing this then to life cycle assessment, again, Paul will go into more depth on the life cycle assessment later on, but just to kind of give an overview, this little image on the left kind of shows how the life cycle assessment, it has these 5 main stages, starting at material extraction, then manufacturing and production, transport, utilization, and disposal. So the life cycle assessment tries to get the full picture of a material from when we take it out of the ground to when we put it back in wherever we put it back. Whereas the carbon footprint generally kind of only covers these 3, the material extraction, the manufacturing and production, and the transportation. You can kind of map how scope 3 would cover the material extraction, scope 1 and 2 would cover what happens in the factory, and then scope 3 again would cover the transport away, but it generally doesn't take into account these other 2. So just to note that the carbon footprint isn't completely extensive. But the benefits of doing a carbon footprint are that it kind of gives you that overview of the whole organization's activities and the emissions associated, which is useful for planning down the line. A life cycle assessment tends to more so focus on like one project or one product, whereas the carbon footprint is for the whole organization. It's also not as complicated to do as a life cycle assessment, so it's relatively straightforward. It's just a case of gathering a lot of data. That would generally be the hardest part, is collecting all the data. And then also in terms of creating a pathway to net zero, measuring a carbon footprint is the first step in creating that action plan towards net zero. Here then I have a sample carbon footprint report. This is from an Irish manufacturer. of a timber frame, roof truss, and posi joint manufacturer in Ireland. It's a factory with 60 employees, and they produce about 400 timber frame units a year. And you see the two small bits on the graph here, the black and the green, that's scope 1 and scope 2. So the heating and the electricity are those two tiny little squares on the left. Everything else is scope 3. So the yellow part is transport and distribution. So that's the trucks taking the timber frames and roof trusses to site. The red chunk is travel. That's all the employees, the 60 employees getting to and from the factory every day. And then you have the little chunk of waste. And then these big blue chunks here, this is all the supply chain. I've just separated them out a little bit by products because it was so huge. But yeah, so the biggest chunk there is the timber, which makes sense given that's their business, is manufacturing timber frames. The next one is construction work, and then metal products, and then other parts of purchased goods and services. But yeah, I suppose the key kind of thing to highlight here is how the supply chain really has a very significant impact on the carbon footprint for a construction industry. And this is the second last slide then, is just how to measure the carbon footprint. So you start off by selecting a base year, which that can be any given year. Going further back in time allows you kind of to analyze the trend. You know, if you could go back to 2010 and bring it up to now, you would have a lot of data to look at in terms of where the emissions might have gone up or down over the years. But data isn't always available that far back. So generally we pick a year where we have all of the data available and fill in from there till now. And as I was saying, yeah, collecting the data is generally the most time consuming part. We recommend using a commuting survey to collect all the commuting data. And also in terms of the procurement data, the purchased goods and services data, it's easiest to sort those by the kind of largest product, like the timber in the last example, or the largest supplier, to just kind of break the data down. And then we also talk about activity data versus spend data. So in the timber, for example, again, if we knew the weight in kilos or even the volume of timber that was ordered that year, that would be a better accurate. You get more accuracy out of that data, basically, if you can get it in weight or volume, as opposed to the amount of money spent on it. But if you can't get it in weight or volume, we do have emission factors for spend, so we can still use that anyway. And then, yeah, these kind of blue bubbles in the middle show what data is needed to complete a carbon footprint. So scope 1 and 2 is basically just your heating and electricity bill for the year. You have to, as well as selecting a base year, you have to outline your boundaries. So whatever factory or number of buildings that you're including in this. So that's the heating and electricity bill for ideally all buildings and factories or units that your company has control over. And then the purchased goods and services is the procurement records. That one tends to be the toughest one to get a hold of and sort through. Travel would, again, that's the commuting survey and any business travel records. Waste is just your annual utility report. And then transport and distribution, a record of the vehicle mileage or the fuel purchased to transport the material goods. And then finally, just kind of the whole reason to measure the baseline carbon footprint. It gives you the chance to kind of analyze where you're at and look for low-hanging fruit in terms of decarbonizing. And then once you have it set out in terms of what you can decarbonize today, what you can do next year, what you can do in 10 years' time, you can kind of put together your pathway to net zero, ideally bringing all those different emission streams down to zero. And then when you have that pathway, you can devise your climate action plan, breaking it down into kind of step-by-step process to decarbonize. And that is the end of this.
So that's a great introduction to carbon footprinting and carbon dioxide emissions, I suppose, and showing the level of emissions that can be associated with your purchased goods and services for an organization. When we would have done it in the University of Galway in a given year, because we built a large building, that emissions associated with that building comes to be nearly similar to all other emissions of operating the university in a given year. And this is a university with 20,000 people, student staff and students, so a very big operation. So we can see that construction has a very big impact on some organizations in terms of their overall carbon footprint, and therefore need to consider it if they're considering a scope 3. So with that, how are we going to decarbonize construction in there? So one of the big parts or one of the main components in terms of construction that leads to large greenhouse gas emissions are the use of concrete and cements. So Dr. Richard Haggerty is going to talk us through about concrete and how we're going to decarbonize it from today, tomorrow, and all the way out to 2050. So over to you, Richard.
So yeah, thanks for the intro. As Jamie mentioned, like the biggest hotspot, I think, when it comes to most buildings is concrete. So what we're going to talk about today is decarbonizing concrete. And today, tomorrow, and 2050, tomorrow being today being obviously what can we do right now, tomorrow being the short-term horizon, and then 2050 kind of longer term. So I think probably the best place to start maybe is a provocative headline from The Guardian in 2019 when they went with this headline, which is "Concrete, the most destructive material on Earth." An interesting choice of word, destructive. I would probably go with impactful, but let's go with their choice of word for now. And yes, it would be the most impactful or destructive, to use their word, simply because it's the thing we use most of. So if you look at this graph, this is a study of the material flows in different kind of countries with different income bands, and you can see that no matter where you are in the world, you use concrete is used. Obviously, different kind of rates and things like that. But you can see by the kind of shaded blue portion, that's your concrete. The darker blue is asphalt. I've included that as well, just to kind of show that there is kind of a difference there in, say, higher income countries versus lower income countries. So we use a lot of concrete, and I suppose the question is, well, why do we use a lot of concrete? And the answer to that is long, but it can be found in this book. So this book is called Stuff Matters by Mark Miodownik. The book was recommended to me by my colleague in UCD, Oliver Cannan, and chapter 3 is called Fundamental. And that whole chapter is about concrete, because that's kind of what concrete is to modern society. It's fundamental. So no matter what you do in your daily activity, concrete is involved in some place. So concrete's important. It has an impact. We understand why we want it. And I suppose the question is, well, for some of you anyway, what the hell is concrete? And this is what you might see if you're in a lab. You might see these blocks like this, or you might see concrete in your building. But just one way I think of looking at it, which can be quite useful, is to look at it from what it's actually physically made up of. So in terms of volume, this is approximately what concrete is made up of. So it's primarily sand and aggregates, about 80%, and then you have a portion of cement, you have a bit of water, and then you have some chemicals. So that is a useful framing if you're a concrete technologist and you're trying to look at what's in the material itself. Seeing as this talk is about concrete decarbonization, I think this can be a useful framing for how to actually look at concrete. And you can clearly see that the big portion of emissions is in the cement. So as noted in the last presentation, cement is a big portion of global emissions. And when it comes to concrete, the biggest portion of emissions is due to the cement. So why is that the case? Well, there's two major sources of emissions when it comes to cement production. Approximately 40-60, this can change depending on your kind of manufacturing process, but approximately 40% is from the energy. So the energy used to achieve the high temperatures required to burn limestone. So the temperature of 1,450 degrees, pretty high. You need typically fossil fuels, but there are other fuels that are used. There's actually some progressive work being done in some Irish cement manufacturers. So like there are ways to reduce that, but the big challenge is this part, which is the calcination. That's conversion of limestone, which has a chemical equation CaCO3 into lime, and what you have left over is CO2. So obviously that's not good. And it's hard to break this because that's just the chemistry of converting limestone into cement. Okay, so in summary, concrete is here to stay, but it has a significant embodied carbon impact. So what can we do about it? I think this is kind of the crux of the presentation, and the framing of it is kind of a 3x3 matrix. Today, tomorrow, as I said, the near-term future, and then the longer term. And then also we've categorized some of the solutions into use less cement, use less concrete, and capture more carbon. Now, I've asterisked the use less cement one because really what we're talking about here is clinker. I appreciate there's different kind of level of knowledge in the audience today. So just to quickly explain, like most cements, the main component of that cement is clinker, which is the product of the cement kilns. You typically then mix that clinker with other materials like gypsum, maybe limestone, things like that. But when we're talking about cement at the moment, we're talking about kind of a high clinker portion cement, maybe a CEM1 or a CEM2 for those who are familiar with the terminology. So right in the kind of top left corner of this matrix, in the use less cement, and what can we do today, especially what can we do in Ireland, is where we can replace the cement with supplementary cementitious materials. The typical material used in Ireland is GGBS, which is a great material in terms of carbon. It's approximately 10 times less carbon than cement. It also has some durability benefits, and there are some differences technically, but this can be done today. It is done today, and it's done in various percentages. The cost fluctuates, but it's approximately a similar price. There's loads of things we could talk about in terms of GGBS. You could have a whole presentation on it, but just one thing I think that's important to point out is that if GGBS is being specified, that it's important to specify it as a cement replacement and not a sand replacement. So you can see here with the two, mix 1 and mix 2, both of those have 50% cement, 50% GGBS, but the important thing here is that you have to also minimize your cement. So if you're using GGBS, ensure that you're reducing the cement content. You're not using the same cement content and just adding in more GGBS. Right, so that's what you can do today. As we kind of move down the line and we start using GGBS, fly ash, natural pozzolan, which are typically used today in different countries, we will run into a problem, which is a supply issue. That's not a problem right now, but it will be in the future, in the short-term future. And what we need to be aware of here is that we don't actually have enough of these materials to completely replace cement. So a bunch of researchers, I think from Switzerland, looked at this from this kind of I suppose lens, and what they saw was they've picked out two materials that they think are kind of going to solve this problem, which is filler and calcined clay. Calcined clay is interesting in that the kind of major deposits in the world are actually in places where the developing world, so where we actually are going to need to develop and use more concrete, there is good deposits of calcined clays. They also note filler. Filler is essentially just crushed limestone. It could be other things as well, but primarily it's kind of limestone fines. I would probably argue that filler maybe isn't the exact same as these in that it's inert, or at least it's partly inert. There is some kind of research questioning whether it does something at an early age, but generally it's not the same as the others, but it can be used and it should be used if you can reach your technical requirements. So that's kind of on the tomorrow side of things. As we head into 2050, I suppose the question is, well, is zero cement possible? And what you're looking at here is a bunch of buildings that have been blown up in Mariupol. And I suppose other than the kind of shocking image, there's another story here. And a lot of these buildings are actually built out of a zero kind of clinker cement. And the cement used here is, so the concrete used is a geopolymer concrete or alkali activated. And this is it's the interesting thing, I suppose, about this is that like the reason for building these buildings out of this kind of no clinker cement isn't because of any wasn't because of any sustainability reasons, was rather because of what was actually available in the Ukraine. So obviously Ukraine is a big steel manufacturing. And obviously there's lots of slag, so they used that and they came up with some interesting innovations in terms of cement and concrete. But again, most of the geopolymers today, they use those materials, which there will be kind of supply shortages. So when it comes to scalable zero cements, we're really at a research stage. So this is just a paper. You can take a screenshot or whatever, and then yeah, have a read of it in your own time. But we're at the research stage when it comes to that. Right. Now into the next row, we're into the kind of use less concrete. And this is important because I suppose the best way to reduce embodied carbon is use less materials. No difference for concrete. So if we can reduce the amount of concrete, that would obviously be ideal. What I'm going to simply refer to you here is an excellent report by WBCSD and Arup. Very simple guidelines on how to actually save concrete in your kind of structural designs. Kind of three of them here, like geometric optimization. You can see in the background that kind of waffle slab idea. You're saving on material there. Obviously your spans for any structural engineers, I'm sure there's loads of them out there. You learn this in your kind of first and second year. See span to depth ratios, and then also your weight versus depth. So there's simple guidelines there of what you can do today. I'm sure many of you do these today anyway, but it's just a matter of pushing them on. In terms of tomorrow, what I've put here is the ultra high performance concrete. So this is an example stadium in France. I think it's a rugby stadium. And that cladding is ultra high performance concrete. This is kind of the show off use for ultra high performance concrete because you can do kind of fancy stuff with it, and that's great. But there is also kind of carbon saving benefits to it. So this is some research we did in UCD on using ultra high performance concrete to reduce the thickness of kind of planar cladding. And what we found that we could reduce the thickness by quite a considerable amount. And when we've published results on this, and what we found was you can approximately achieve about 40% carbon saving by reducing or by using UHPC instead of standard concrete for cladding. Now, our mix was optimized for kind of embodied carbon as well. We did use GGBS and we did use some limestone as well. But there, just to give an example of some of those savings. As we enter into the 2050 kind of realm, I'm probably being a bit harsh here saying this is 2050 stuff. This could technically be done today, but this is kind of, you're talking about kind of serious geometric optimization here. So there's a kind of research group in ETH Zurich, which have been kind of looking at this for maybe a decade now. They've been optimizing this. There is real case studies now of using this kind of technology where they're mixing concrete technology, but also this kind of geometric optimization of the form. So like the reason a slab is rectangular is not because that's the optimized geometry, it's because that's the easiest thing to make. So these guys are looking at this and seeing how they can kind of optimize that geometry. And there's other research groups looking at this sort of thing as well. So now into the capture more carbon. Just before I kind of get into it, I'm not talking here about carbon capture, storage, and utilization of cement factories. That's kind of a separate topic and could be discussed maybe in a different talk. I'm kind of talking about capturing more carbon in the concrete itself. So if you bear with me for a second, just a little bit of chemistry. So at the start, I showed you what calcination is how you make cement ultimately. You have limestone, and then you have lime, which is the precursor to clinker and cement, and you have CO2 left over. We obviously don't want that. So the question then is, can we reverse the chemical process? Can we do that? And yes, we can, and actually has a name, and it's something that happens. It's carbonation, and this actually happens with normal concrete anyway, but it's typically a very small percentage of what was actually emitted. So just in the, I suppose in the today, what can you do today? There are some companies in Ireland that are actually using this. So it's Carbon Cure. It's a technology which saves approximately 4 to 6%. And they do it by injecting the material into the concrete during batching. So obviously an advantage of this is that it's quite simple and it's handy in that sense. It's obviously a small saving. So obviously there has to be caution that if using such technologies that you're not actually increasing cement or things like that. I'm not sure that happens, but it's just worth noting that for any kind of marginal saving when it comes to decarbonization, you just want to ensure that you're really not like increasing it on another kind of direction. In terms of the tomorrow kind of ideas, there's this technology called Solidia, which kind of combines two technologies, maybe we could say. So part one is CO2 curing. CO2 curing is actually used typically today. So that's used to kind of in precast concrete to cure concrete, but typically it only absorbs a small amount of CO2. So with this technology, they've also optimized the materials, and by doing so, that absorbs more CO2. The problem with this kind of technology is, again, that scalability issue. But at the start, we kind of talked about the fact that cement is only a small portion by volume. And if we're talking about kind of capturing carbon, should we not really be focusing on this kind of portion? Can we not create sands and aggregates which absorb CO2? And there is a company that are looking at this I think in the US called Blue Planet, not to be confused with David Attenborough. But what they're doing is they're kind of generating these kind of synthetic limestones. Again, not the technology behind it's not completely clear, but the concept is interesting, right? Because the thing we use most of is concrete. If we have to capture carbon in the future and utilize it, that utilization portion, I think concrete makes for an interesting kind of case study. So this is kind of a lecture in CPD I do in UCD and RKD, but every time I do it, I kind of have to update it because there's always new kind of research, and there's two technologies I'm going to quickly talk about, which have emerged, well, on my radar recently anyway. Maybe they've been out there for a long while. But first is this sublime systems. So it's interesting technology in that the innovators of it are cement chemists, and they kind of looked at what's the end result of cement, and it's this calcium silicate hydrate paste, and they're kind of thinking, why are you doing it that way? This would be a more efficient way. This way being this kind of electrolytic reactor. Don't ask me what that is. I don't really know. But what's interesting in it is that it uses electricity and it uses non-carbonate materials. So that's kind of interesting. Check out their website. It's really good, really interesting. Lots of detail there. And then there's this one which has emerged recently, which again is very interesting. I think it's obviously caught a lot of attention. Friends of mine who don't know anything about concrete or have no interest in concrete are sending on to me. I think electric cement has a nice ring to it, and then also that Cambridge portion. But it is interesting, and what they're doing is they're replacing the flux used in kind of electric arc furnaces with recycled cement paste, and that is interesting. I think scale is again going to be a challenge here, but certainly an interesting technology to look at. I think another thing they note in the paper is that the quality of product also depends on the input of that kind of recycled material. So that's kind of the overview of the kind of presentation in terms of decarbonizing concrete. I also just want to refer to the report that Jamie mentioned at the start, which is a report led by RPS with ourselves in RQD and EY. And if you're looking for some detail on how to procure low carbon concrete, you will find it there. So thanks for that.
Sure, that's a great run through. So some ideas there around decarbonization of concretes and cements today and in the near future and the long-term future. And Richard could probably have talked again for another hour with lots of other options in there as well. But that just gives a flavor of some of the things that are there. So I'm going to move on to our third presenter now. So third presenter is Dr. Paul Moran, who's an assistant professor at the University of Galway. And he's going to talk about assessment of whole life carbon of case study buildings in Ireland using the Indicate 2.
Okay, hello everybody. Thanks for coming along to today's session. So I'm just going to present on behalf of Stephen Barrett, who, as Jamie mentioned, couldn't be here today. But essentially, this is the results from a project between ourselves here in University of Galway and the Irish Sustainability Council, where we went about assessing or developing a methodology to assess the whole life carbon associated with the way we're constructing our buildings right now in Ireland, and then developing up baselines for kind of where we're currently at. So in order to do this project, we needed a lot of help from industry. So together with all these organizations here that are presented on the slide, we were able to compile our results for the 50 different case study buildings. So we're very much appreciative of all these different organizations for helping us out as part of the project. So by 2030, with the introduction of the new EPBD, essentially now we are required to start assessing the carbon associated with the life cycle of our building. So that's going from the extraction of the materials that we use in the buildings themselves, all the way through the entire life cycle to when the building is then recycled or demolished then as part of. So we're from our A1 to A3 is essentially developing up our products and the products we use in our buildings. They're from A4 to A5 associated with bringing those actual products and materials to site and then construction the actual buildings. Then we're talking about the operation of the building in our B stage, and then actually maintaining and refurbishing that building then throughout its entire life cycle. Then from stages C1 to C4 is essentially the demolition or removal of that building, and then D is the recycling of all the materials associated with the building itself. So essentially, we need to start assessing the carbon associated with each of these different stages of a building's life cycle. There's been a good bit of different research done on the embodied carbon associated or the life cycle carbon associated with our buildings, but there hasn't been one standard approach to how these studies have calculated their carbon. So as part of the projects that we're working on, the first task was developing up the methodology to assess the carbon. And then once we had this methodology developed up, we then applied it to all our different case study buildings. So to assess the carbon associated with all these different stages, we essentially needed a series of bill of quantities for the various different buildings, and then using the best available data sources that we could find that would be relevant to Ireland, we then set about assessing the carbon associated with each of these different stages. So for example, from A1 to for the A1 to A3 stage, using the bill of quantities of all the different buildings and using a database of carbon associated with different building material products. We then were able to calculate the carbon associated with A1 to A3. So then taking assumptions from various different sources, as I mentioned, we then set about calculating the carbon with all the different stages of the building's life cycle. So essentially, the crux of the tool is you have to enter in the quantity of material in kg for the materials going into the building, and then using EPDs or using a carbon factor from our database, you then are able to calculate the carbon associated with that particular material, that particular product. From the MEP side of things, that is quite a challenge right now in calculating the carbon associated with that, and it's probably the biggest limitation that we have right now, just with the way that data is available right now and the way that MEP is reported, and then also the carbon associated with the MEP itself. So that is a challenge that is currently existing in this area and something we're trying to address now moving forward. Then as well as that, we ask the users to estimate or input the energy demand of the building per annum, and then any refrigerants or water requirements that the building also has. So taking all these different sources, we then are able to calculate the carbon associated with the building then throughout its entire life cycle. The tool itself then gives a breakdown of the upfront carbon with the way that we construct our building. So how much carbon we use to produce the products, and then how much carbon required to transport the products to site and construct the building itself, and then the whole life carbon as well. So we are able then to break down essentially where the carbon hotspots are associated with the building. So within the tool itself, you assign the material product to a specific area of the building, and then at the end you were able then to identify where all the different hotspots are within the building itself. Then using this approach, you were then able also to calculate how complete your LCA is of your entire building. Again, this just adds transparency to how much of your bill of quantities you actually set as part of your assessment. And then it also helps us when we're verifying and reviewing any assessments that are sent back to us to make sure that everything is to a high quality standard. On the top left here, again, we have our completeness level of our assessment, but also we have a data quality score. So again, we have to be able to assess these assessments that are all being sent back to us. So the data quality is obviously impacting kind of the way that we consider all the benchmarks that we're developing as part of our assessments. So the more generic data that you use as part of an assessment, the lower data quality score you will have. And if you were able to rely on more EPD-based information, the higher data quality score you will have. And again, that just helps us then consider how accurate then your assessment might be then as part of the project. The tool then will give you kind of a breakdown of all the different tiers or all different elements of your building. So from your substructure, structure, non-load bearing elements, roof, fittings, etc. And again, give you a breakdown of the carbon associated with them, and it'll tell you what is the most impactful materials that are currently within your building design. So we also have a draft template report that the tool will provide to you after you've kind of gone through the assessment as well, giving you a summary overview of where the carbon is associated with your building as well. So the data that we have right now, in terms of the amount of mass within the buildings that we have assessed, there is a lot of concrete and cement. Nearly 75% of all the 75% of all the, in terms of mass, is associated with carbon and concrete and cement, and then 7% is associated with steel. When we look at the A1 to A3 carbon associated with our buildings, concrete and cement are currently contributing to 41%, with metals and steels have 36%. So having a big impact in the way that we're currently designing our buildings. So here we have the results of the different typologies that we assessed broken down. So we did an initial 20 case study buildings as part of the project. And again, we broke them down across the different typologies in terms of how much of carbon they were having an impact from your A1 to A5 stage, and then for the remainder of the whole life carbon or the whole life cycle of your building as well. So based on the 21 to 20 case study buildings we initially assessed, we were getting an average of about of 610 kilograms CO2 equivalent per meter squared for your A1 to A5, and then 407 for the remaining stages of the life cycle. Then we got the number of case study buildings increased from our 20 to 50, and our averages reduced. So in terms of mean average, we are now at around 546 kilograms of CO2 per meter squared for upfront CO2, and 279 for the remaining stages of the building life cycle, which is which is similar to results that the UK are finding, where they got 568 for their A1 to A5 stages for similar projects that they carried out over there. So the more case study buildings that we can start to compile as part of these, the better kind of benchmarks we can then start to set moving forward, and how we start to reduce the carbon associated with our buildings as well.
Thanks, Manny, for that presentation, Paul. It was great in there. So working through, I suppose, highlighting the whole life cycle carbon assessment of buildings, and showing that by having this case studies, we're using a common tool or common method, that it makes it much more transparent, much more clear. We can set some baselines associated with that, and you can see it in different topologies in terms of, say, residential, how they have a different amount of carbon associated with the construction phase and the maintenance phase of those buildings in there. And also, when you have, say, 15 apartment blocks done, you can actually see where somebody's left out, say, landscaping, someone else might have left out building services. You can also see what the actual whole carbon is when you take everything into account, once you have enough case studies into the database in there. So I think, Paul, you're still collecting up case studies. So if anyone is interested in collaborating on this, Stephen Barrett and Paul, who are working on the project, would be interested in helping support consultants to do some whole life cycle carbon assessments of buildings.